Welcome to lecture number 7 of our system protection course. In the last class, we discussed about the voltage transformers, the transient response of voltage transformers, and also we talked about the ratio error, phase angle error of a voltage transformer, CCVT, through some examples. We demonstrated it. And also, we have seen how to design a CCVT. So all these things we discussed, and that in fact completes your CTVT. And in this class, we'll talk about the fault analysis. So fault analysis, I hope already you have studied in your last course or in any previous courses. And fault analysis, in fact, plays very important role in designing the relay coordination system or relaying system, or in power system protection. So, what is fault analysis? What we do in this? In fact, there are various types of faults we have seen, like 11 types of sound faults. And broadly, we categorize these faults into two types. One is, we call it symmetrical fault, and second one is your unsymmetrical fault. So for symmetrical fault, it is very easy to analyze because when the symmetrical fault happens, there is no unbalancing in the network, unbalancing in the voltage and current and power. So therefore the analysis is similar to the steady state analysis, and it is very easy to do. Whereas when the unsymmetrical fault happens, in that case, what happens in unsymmetrical fault, everything becomes unbalanced. Your current, voltage, power, everything becomes unbalanced, and hence the analysis that, because in general in steady state analysis, steady state three-phase analysis, we took the single line diagram and we do the analysis like already you have done in load flow analysis, all these things. But in case of unsymmetrical fault means like single line to ground fault or double line fault, double line to ground fault. These are unsymmetrical fault. So in case of unsymmetrical fault, in fact, it becomes very difficult to do the analysis. And how to proceed then? How to do this analysis? So let us see in this lecture. Um, in fact, we use the sequence components for unsymmetrical fault analysis. So let us see then how sequence components plays very important role in unsymmetrical fault analysis. So what is sequence component? Already you have studied. I'll just introduce little bit, and in fact in this lecture we'll finish this fault analysis of unbalanced faults using the sequence components. So let you know that we have three sequence components. One is your positive sequence components, and other one next is your negative sequence component and zero sequence component. So in fact, if we'll see these sequence components, they are in fact balanced phasors, right? They are the balanced phasors. You can see here the positive sequence component is quite balanced. It is in fact similar to the steady state phasors, right? And the negative sequence component is also, it is balanced, but the sequence is exactly opposite to the positive sequence. You can see here for the positive sequence, the sequence is exactly like your steady state condition, right? The sequence is A, B, C. Okay, but in case of negative sequence, we'll see the sequence is A, B, and C, that is in anti-clockwise direction. Here it is in clockwise direction, but here it is in anti-clockwise direction. And the zero sequence components, they are also balanced. They are equal in magnitude, but they are in same phase, right? We can see here they are in same phase, A0, B0, and C0. So we represent these phasors in terms of 1. So in positive sequence, we represent in 1. The subscript will be 1 always. And in negative sequence, it will be 2. The subscript will be 2, and zero sequence, the subscript will be 0. Okay. So then what we'll do during unbalanced case, when the unbalanced fault happens, we have to represent the unbalanced phasors, voltage phasor, current phasors in terms of these three components. So that will make our analysis easier. And that is the only motivation behind using the sequence components in unbalanced fault analysis. The main motivation is just to the make the analysis easier. Okay, so that is the only motivation. So let us see the components. So as I told that the phasors will be unbalanced phasors will be represented using the sequence components. Here let us say we have the phasors VA, VB, and VC, and now I can represent each of the phasor. VA will be represented using the sum of the sequence component phasors VA1, VA2, VA0. So VA1 is the phase A voltage in the positive sequence component, and VA2 is the phasor in the negative sequence component that represents the phase A, and similarly VA0 is the phasor component of the zero sequence component that represents phase A. Similarly, we can represent the phasor quantities in phase B and phase C, right? So phase B will be represented as VV1, VV2, and VV0, and VC will be represented as VC1, VC2, and VC0. Okay. So this will give us that we are representing unbalanced phasor in terms of the balanced phasor quantities, right? So now I want to represent all quantities in phasor B and phasor C in terms of the quantities in phasor A only, right? So how can I represent? Let us see then. So now I can write VA equal to, it will remain as it is, VA1, VA2, and VA naught, and similarly VB I'll represent, because VAO equal to VBO equal to VCO, so these will remain same. So VBO, instead of VBO I can write VAO, and instead of VB1, how can I represent VB1 in terms of VA1? VB1 will be equal to, here we can see in this phasor, VB1 will be represented in terms of VA1. How I'll represent? In fact, there is an operator, we call it A operator, which is here, right? These are A operators. So A operator is nothing but this quantity. A is nothing but A is equal to e to the power j of 2 pi by 3, that is nothing but 1 of 120 degree. That means A is represented as the magnitude 1 and phase angle 120 degree. Okay, so now if I'll take VA1 as the reference phasor, then VB1 how I'll represent using VA1? I can write VB1 as BA1 phasor into angle of 240 degree, because it is a difference of 240 degree. We can see here 120 and 120. So there is a difference of plus 240 degree between VA1 and VB1. So I can write this as VB1 is equal to VA1 240, and I can write this as VA1. So I can write this as A square VA1. Okay. So A square is nothing but A square is equal to 1 of 240 degree. Okay. So now I can represent VV1 as A square VA1, right? So similarly, I can represent VB2 here. VB2 is having phase difference of 120 degree with respect to VA2. So therefore, I can write it as VB2 is equal to, I can write VB2 is equal to A of VA2. Okay, so that is what we have here. It is substituted. That means your VB1 VB1 is represented or substituted as A square VA1, and VB2 is substituted as A of VA2. Okay, and similarly your VC1 is represented as A of VA1, and VC2 is represented as A square of VA2. Now substituting these values, we'll get this matrix. Okay, now I can represent VA1, VB1, VC1 as a multiplication of a matrix into VAO into VAO, VA1, VA2. So this matrix is known as the transformation matrix. Okay, transformation matrix. Okay, now if I'll represent the sequence components, that is VAO, VA1 and VA2 in terms of the unsymmetrical voltages VA, VB, VC, because these are the known quantities VA, VB, VC. These are known quantities, and we want to do analysis in the sequence components. So therefore we need to transform the phase quantities into the sequence quantity. So therefore I can write VAO, VA1 and VA2 in terms of VA, VB, VC by just taking the inverse of the transformation matrix. So by taking the inverse of the transformation matrix, so easily we get it. So it will 1 by 3, you can check it, 1 by 3, 1, 1, 1, 1 A square, 1 A square A. So just little change in the transformation matrix. It is multiplied with 1 by 3, and the elements have been just swapped between the second and the third column. Okay, so or you can say uh, second and the third row, same thing, right? Okay, so now we'll proceed. So now let us find the sequence network of a few of the components of the power system, like loads, generators, transmission lines. And let us first see how to find the sequence networks of impedance loads. So if we have symmetrical impedance load, you can see here we have symmetrical impedance load ZY, which is connected in the star fashion. So in each phase the value is ZY, right? Okay, and the neutral is connected through the ground with an impedance of Zn, and the voltage is applied, the phase voltage is applied across each of the phases VAG. VAG is the phase to ground voltage, in fact not phase to neutral voltage. Okay, so VAG is the phase voltage between phase A and the ground. Similarly BG is the phase voltage between phase B and the ground, and VCG is the phase voltage between phase C and the ground. Okay, so now our objective here is to represent these impedances in the sequence form. So how we'll do that? We'll just write the network equation for this network, and then we'll use the transformation, then we'll find it easily. So let us see how we can do it. So that the question is here, derive ZS. ZS means the sequence impedance, ZS. Now the answer is this. Sorry, this is the equation, network equation, right? So the network equation, if we'll write for this network, I can write VAG. So if we'll write VAG, let me write it. VAG will be equal to IAG ZY, sorry, ZY, okay, or IA, simply you can write IA ZY plus INZN, right? And just by expanding IN, I can write this as IA plus IB plus IC into Zn, right? So now I can see here that VAG I can write ZY plus Zn into IA plus Zn into IB plus Zn into IC, right? This is the equation for VAG, okay? Similarly, we can write the equation for VBG and VCG. So after writing all the equations, we can write it in the matrix form in this form, right? Okay, so we can write it. Now we'll convert this into the sequence form. How we'll do it? So just take the just convert it into sequence form. So both sides, let us multiply the inverse of the transformation matrix. Okay, so let us multiply. Or how we can write this equation in terms of this multiply the let represent the transformation matrix as T, that is nothing but 1 1 1 and 1, sorry, 1 a square a 1 a square, right? Already we have seen. So already we have seen T equal to that, right? Just represent VAG, VBG and VCG in terms of VO, VO, VAO, VA1 and VA2. Okay. So if we'll write in terms of this, how we'll write this? We'll write it as T of VO12, right? So O12 is nothing but VO, V1, V2. This I am representing as VO12 as matrix, right? So that is nothing but equal to VAO, VA1 and VA2. Okay. So I am taking that this VAO, VA1, VA2 must, let us represent this as VO, V1 and V2. Simply these are the zero, positive and negative sequence voltage of phase A. Okay. So now let us represent this. So I'll multiply this, and this is nothing but this is your VABC, right? Okay. So let us then convert, and this Z impedance I can write it as ZABC into or simply write ZY. Okay, it is better. So ZY into T of IABC. Okay. Now what we need to do, just multiply T inverse at both the sides. So it will become T inverse, sorry, T inverse. So T inverse T will become identity matrix. So it will give us VO12, right? And the rest of the equation will be T inverse ZY, sorry, ZY into T, right? into IABC. Sorry, this is not IABC, this is I012. So this will be I012. Okay. So now, just by multiplying T inverse with ZY with T, because so it will give us the sequence impedance. So therefore, the sequence impedance is nothing but, now I can write it here, the ZS sequence impedance is nothing but, that is T inverse ZY into T. So this is your sequence impedance. So just by multiplying T inverse with ZY, then multiplying T, the transformation matrix, will get the sequence impedance. So this is the process to get the sequence impedance. Now we can see here, because this is a balanced load, so we can see here the sequence impedance. ZO will become ZY plus 3ZO. Z1 will be equal to 3 ZY, and Z2 will become equal to Z1 equal to ZY. So your equation will become, in that case, that is BO, sorry, let me write it here, BO V1 V2 will become equal to ZO 0 0 0 Z1 0 0 0 Z2. So this is your sequence network. So it will become IO, I1 and I2. Okay. So now this is your sequence impedance matrix ZS. Okay. And already we know that when we'll multiply the transformation matrix, that is ZS is nothing but it is equal to the T inverse ZY into T, right? So this will give us these values. So Z0 will be equal to ZY plus 3ZN, and Z1 will be equal to ZY, and Z2 will be equal to Z1 equal to ZY. Okay. So now we can see from this equation that all the equations are really uncoupled. They are not coupled at all, right? If I write these equations, I can write VO equal to ZO IO, right? And V1 equal to Z1 I1, and V2 equal to Z2 I2. So they are uncoupled. Now these equations, uncoupled equations, if we represent through the network, so the network will also become uncoupled, right? Okay. So now we can see, if we'll represent these equations through the network, if I'll represent zero sequence network, which will represent this VO equation, right? So this will be VO equal to IO into ZY plus 3ZN. ZY plus 3ZN is nothing but it is equal to ZO. Similarly, if I'll represent the V1 equation, which will represent the positive sequence network, so it will become V1, that is equal to nothing but I1 ZY. So ZY is equal to Z1. Similarly, if I'll represent V2, that will represent the negative sequence network, and that will be V2 equal to I2 ZY. Okay. So this is how we convert different components into the sequence components, right? So just by writing the equations in the process is, first you have to write the network equation in terms of the phase domain, or in the phase domain, then you convert the phase domain equation into the sequence domain, and after conversion just represent the sequence domain equations into the networks, and that will represent the sequence network. Okay, it is easy, right? And in the sequence network, it is very easy to do the analysis, right? Okay. So now let us see the sequence network of series impedances, how we can represent the series impedances. In the same fashion we have to proceed. So here we have a transmission line. So this is the phase A line, and this is phase B line, this is phase C line. So phase A is represented with voltage at the receiving end VAN, at the sending end VAN, and at the receiving end it is VA dash N. Similarly, for phase B, the sending end voltage is VBN and the receiving end voltage is V dash BN, VV dash N. Similarly, for phase C, the sending end voltage is VCN and the receiving end voltage is VC dash N. So now we'll represent these impedances ZA, ZCC, ZBB, and also if some mutual impedance is existing between these two. Suppose this is VCA and this is VC, not V, sorry. This is your ZCA, and this is ZBC, and this is your ZAB. That is a mutual impedance if it is existing. If we are taking into picture the mutual impedances, then your equation will become like this. Okay. So the equation if we'll write, we can write VAN minus VA dash N, that is the voltage drop across that line of that transmission line, that will be, let us represent it as VA dash, then I can write that as VAA into IA plus VAB into IB, VAC into IC, right? Similarly, all other equations I can write in all the transmission lines in each of the phases, in phase B and phase C, right? So then I can represent all these three equations in the matrix form, and that will give us this matrix form, right? So now we need to convert these phase domain equations into the sequence domain equations by just representing these phase domain quantities in terms of the sequence domain quantities, as we wrote in case of the impedance load in the previous slide I have shown. In a similar way, we have to write the equations, and after writing those equations, we'll find the final sequence network. This will be your final sequence network for zero sequence network. This is for positive sequence network, this is for negative sequence network, right? So you can try it in your home also, you can try, and you will find these equations, right? So if you write these equations, it will be simply, just I'm writing the final equation in the sequence domain, that is VO, V1, V2 will be equal to ZO 0 0 0 Z1 0, sorry, this will be 0 0 Z2 into IO, I1, I2, where your ZO is equal to ZA plus 2 ZAB and Z1 is equal to ZA minus ZAB and Z2 is equal to same ZA minus ZAB. So it has been assumed that ZA is equal to ZBB equal to ZCC. Okay. So it is assumed that the length of the line is same. Okay. So this is how we get the sequence network for a transmission line. Now let us see the sequence network for the synchronous generator. It is in the same way also we'll derive this, right? So this is the equivalent representation of the synchronous generator in the phase domain, right? So in the phase domain, it is the representation. So these are the let us say ZS, synchronous impedance of the synchronous machine, and Zn is the impedance through which the neutral is connected to the ground. Okay. So now we need to derive the sequence network. Already you know the process. I hope you can do. And find the expressions of ZO0, ZG1 and ZG0. I hope you can do this because very simple. Just write I'm writing the fundamental equations in the phase domain. You can write other equations, right? So let me write it. So it will be, if I'll write it, it will become, because EA, EB, EC, they are the generated voltages and they are in fact always balanced, right? They are balanced quantities. Okay. So EA, EB, EC, they are the balanced quantities. EA, EB and EC. And therefore let us, at the terminal voltage may become unbalanced because of some fault, some disturbances. So let us represent the terminal voltage in terms of the phase voltages, in terms of the generated voltages and other parameters like current and the impedances, right? So let us represent this. So I can write VA, VB and VC. So let us write first equation for VA. It will be EA minus ZSIA, then minus ZNIN. So ZNIN, in fact, IN I can write in terms of IA, IB, IC. I can write it as IA plus IB plus IC. Okay. Similarly, for VB, I can write EB minus ZS IB minus Zn IA plus IB plus IC. Okay, similarly for VC I can write EC minus ZS IC minus Zn IA plus IB plus IC. Okay. So if I'll represent this in the matrix form, I can write this as VA VB VC, that is equal to EA EB EC. Okay, so minus ZS plus Zn, ZS plus Zn, 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 ZS plus Zn, Zn, then Zn, Zn, ZS plus Zn. So this is the impedance matrix into IA, IB, IC. Okay. So now you can, this is your IC. Now you can convert the phase quantities into, just represent the phase quantities into the sequence, in sequence quantities, right? So if I'll represent the phase quantities in sequence quantities, what I'll find? So let us represent this as Z, Z of syn, okay, synchronous machine impedance. Okay, I'll represent this impedance as Z sync. Okay. So now how can I write? Sorry, I can, if I write the phase domain quantities in terms of the sequence domain quantities, I'll write T into V012, okay, equal to T into E012 minus this is your Z sync into T of IAVC. Okay, sorry, not I, I012. Okay, now just multiply T inverse both the sides, so it will become V012 and this will become EF012 minus T inverse Z sync T I012. Okay, so now this will represent, this will give us Z of 012. Okay, Z of 012 will find from this T inverse Z sync into T. Okay, now what will be the what will be the value of this E012? E012 will be nothing but, because the positive sequence component, the zero sequence component of this is a balanced phasor, so the zero sequence component will become 0. Okay, and the positive sequence component only will exist E1, and negative sequence component will also be 0. Okay, so this is the phase. Okay, so now E1 will be obviously equal to EA, that is equal to EB equal to EC, that is the magnitude. Okay, so that is equal to EA, simply we can write EA. Okay, so now after multiplying T inverse with Z sync with T, we'll get the Z0, Z1, Z2. Now I'll represent the synchronous machine in terms of the sequence network by just multiplying and finding. Just I can write the equations. So the final equation I'll write, the final equation will be VO, V1 and V2, which is nothing but it is equal to uh, uh, E of 012, that is nothing but 0 EG1 simply you can write EG1 0 minus ZGO plus 3Zn, then 0 0 0, here is ZG1 0 0 0, ZG2 is multiplied with IO, I1, I2. So these are the uncoupled equation, and these uncoupled equations are in fact represented by the uncoupled sequence networks for zero sequence, positive sequence, and negative sequence. Okay, so we can see here that these quantities in fact are represented in terms of zy and, or you can say zs and zn. So you can find it by just multiplying T inverse Z sync and T. So you'll find these values. Okay, we're not going to discuss this. You can calculate this. Okay, so now we'll see the unsymmetrical fault analysis using this. Let us see the. Now we'll see the unsymmetrical fault analysis using the sequence components. So first let us see the assumptions taken in the unsymmetrical fault analysis. What are the assumptions? So generally the power system operates under the balanced steady state condition, right? So before the fault occurs, and thus the zero, positive and negative sequence networks are uncoupled. They're uncoupled, we have seen. If the network is balanced or the condition is balanced, then I will represent those networks that will be represented through the uncoupled sequence network, right? So before fault, in fact, we represent, if we'll represent it is in fact the uncoupled sequence network before the fault occurs. So during unsymmetrical faults, they are interconnected only at the fault location. Okay, so only during the unsymmetrical fault, they are interconnected at the fault location. So pre-fault load condition, load current is neglected. So let us assume that the pre-fault load current is neglected, and because of this, the positive sequence internal voltages of all the machines are equal to the pre-fault voltage Vf. Therefore, the pre-fault voltage at each bus, okay, so please note here the positive sequence internal voltage will all the machines will become Vf, along with the pre-fault voltage at each bus also it becomes Vf, right? Please note, will represent during fault, so just before the fault the voltage at the fault point is Vf. It is the assumption, okay. Now the third assumption is the transformer winding resistances and the shunt admittances are neglected, okay. Then the fourth assumption is transmission line series resistances and shunt admittances are neglected. That the only by considering these last two assumptions, that is assumption 3 and 4, we can say that the voltage remains same at each of the bus just before the fault, and that is equal to Vf. Okay. So now let us go ahead with analysis. First we'll consider the single line to ground fault. So in case of single line to ground fault, let us see. So this is your network, right? This is your whole network, and we are considering the point where the fault is happening, and other two terminals they are remaining open. Suppose let us say the fault is happening at terminal A, at phase A, that is single line to ground fault, right? And phase, let us say the phase B and phase C, they are open, that is IB equal to 0 and IC equal to 0. Now what are the conditions, fault conditions in phase domain now during the fault? So during the fault, we'll see, if we'll see at the phase A, the voltage at phase A will be VAG, that is equal to ZFIA, right? So this is the current flowing through this fault impedance, ZF is IA. So that ZF is in fact the arcing impedance, right? So VAG will become equal to ZFIA, and at the other terminal VB and VC, sorry, B and C, your current, that is IB and IC, they both will become equal to 0. So these are the fault conditions in the phase domain. Now we'll convert these conditions in the phase domain into the sequence domain. I will convert this, just substitute the values in terms of the sequence domain quantities. Okay. So now let us see. So if we'll represent the sequence components, that is IO, I1, I2 in terms of IA, IB, IC, just substituting IA, IB, IC, we know IB equal to 0, IC equal to 0. Now the only term will be IA. Now if we'll represent, then your equations IO1, IO, I1 and I2, they all become equal, and that is equal to 1 by 3 IA, right? So I can write here the equation for VAG. So VAG I can represent through VO plus V1 plus V2, and that will become equal to ZF into IO, because it is multiplied with IA. So IA is nothing but it is equal to IO plus I1 plus I2. Now the fault conditions in sequence domain, what will happen? Already we derived that IO is equal to I1 equal to I2, right? That is nothing but equal to 1 by 3 of IA, right? And also from this equation, we can say that because IO plus IO, I1, I2, they're equal, just substitute I1 here, 3I1. So it will become 3ZF I1, right? So from this equation, we'll get this, that is VO plus V1 plus V2 equal to 3ZF I1. Now these two equations, can you represent these two equations by using some sequence network, right? So that means the current is same, because in all the three sequence networks, the current is same, means they are all connected in series. Okay, and the voltage equation, the voltage, it represents VO plus V1 plus V2 is equal to 3ZF I1. So we can represent this very easily in a series connected. The three sequence networks are connected in series, and the voltage across the series network will be 3ZF I1. So let us see the network then. So this is another equation. We'll see that this equation will be derived from the sequence network. We can see the sequence network here, right? So the sequence network is here. This is your sequence network. So the sequence network is, we can see here, this is your zero sequence network, this is your positive sequence network, this is your negative sequence network, right? And already we know the VF is the pre-fault voltage, just before the fault voltage is VF, and that is in fact embedded in the positive sequence network, right? So now these three sequence networks, zero sequence, positive sequence and negative sequence networks, they are connected in series because the current is flowing, because the currents are same, equal. I1 equal to I2 equal to I0, and the voltage across the series network is 3ZF I1, right? So the voltage across this is equal to, that is VO plus V1 plus V2 is equal to nothing but, that is equal to 3ZF I1. So as the current I1 is flowing through the 3ZF, so the voltage across this will be 3ZF I1. And now from this equation, if I'll write the equation for, from this figure, if I'll write the equation for I1, how can I represent in terms of VF and other Z parameters? It will be simply VF by ZO plus Z1, ZO plus Z1 plus Z2 plus 3ZF, 3ZF, right? It is very simple. From the network, from the sequence network, we can derive. Now we can derive the other parameters also from the sequence network, and this gives us in fact the analysis, the analytical result for the single line to ground fault. And after finding the fault current in the sequence network, again we'll convert to the phase domain, and that will give us the fault current in the phase domain, right? So so the analysis becomes very simpler, right? Similarly, if we'll consider the line-to-line fault, let us see the figure. Here the network is given, and the line-to-line fault is happening between the phase B and phase C. It is arcing fault, and the arcing impedance is ZF. Okay. So now if we'll write the fault conditions in the phase domain, I can write it as similar fashion: IA equal to 0, and IC is equal to minus IB, and the voltage difference between this will be equal to ZF IB. So therefore I can write VVG minus VC is equal to ZF IB, right? Okay. So now I will write just in the sequence domain the equations. So if I write IO, I1, I2, that I can write the inverse of the transformation matrix, that is multiplied with IA, IB, IC. So IA is 0, and IB we put IB, and IC instead of ICO we put minus IB, right? So now I can, after multiplying this matrix with this, I can write 0, 1 by 3 A minus A square IB, 1 by 3 A square minus A IB. So now from this equation, it is very easily we can understand that IO equal to 0 from this equation, and I2 becomes equal to minus I1, right? Okay, I naught is equal to 0 and I2 equal to minus I1, right? And now from the voltage equation, from this equation VVG minus VCG equal to ZF into IB. So from that equation I can write, just substituting the sequence quantities, instead of VVG I can write VO minus A square VA1 plus AV2, and instead of VCG I can write VO plus AV1 plus A square V2, and then that is equal to ZF IB. IB is nothing but equal to IO plus A square I1 plus AI2. So now what we'll get? We'll get A square minus A into V1, just from this equation, right? A square minus A into V2 equal to ZF A square minus A I1, right? Now A square minus A will be cancelled both the side, and it will become V1 minus V2 is equal to ZF I1, right? So this is one of the equation. So now under fault condition in the sequence domain, what are the equations we found? The first equation is I not equal to 0, and second equation we got I2 equal to minus I1 from the here, and then V1 minus V2 is equal to ZF into I1, right? So now if we'll see these quantities, these equations, if we'll represent these equations using some sequence network, sequence component networks, then how it will look like? So that means we can see that from these two equations that I positive sequence and negative sequence networks, they are interconnected, but zero sequence network is disconnected because I naught is equal to 0. So therefore the zero sequence component was segregated, it is separated, it is because I naught equal to 0, and positive sequence and negative sequence component, they are connected together, but the currents are flowing in the opposite direction, so that your uh, I1 is equal to minus I2, and V1 minus V2 will become equal to ZF into I1, right? Okay, it's very simply we can represent this. Okay, now from this network, how will find I1? How will find I1? So I1 will be equal to minus I2. That will be nothing but VF by Z1 plus Z2 plus ZF. Very simple. That is equal to I1, and that is equal to minus I2, right? Okay. And IO is equal to 0, obviously, from the zero sequence network, right? Okay. So this is very simple, line to line fault. Now we'll see double line to ground fault. So for double line to ground fault, this is your network, and both the phases, phase B and phase C, they are sorted and they are connected to the ground through the fault impedance ZF, right? So in a similar way we'll proceed, that is, first we'll find the conditions, that is the fault conditions in the phase domain, then we'll convert it into the these are the equations in the phase domain, fault conditions, then we'll convert it into the sequence domain, then those sequence domain equations will represent in the sequence component network form, and from the sequence network component we'll find the fault current. Okay, so the same way we'll proceed. Now IA equal to 0, I can write it here, IO plus I1 plus I2 equal to 0, and similarly the voltage VV equal to VCG, that is equal to ZF IB plus IC. Just substituting the quantities, sequence quantities, we'll find this, and then ultimately we'll find that V2 equal to V1, right? So from here V2 equal to V1, and also by substituting this ZF into IB plus IC, we'll get that VO, that is nothing but equal to VVG. So VV is equal to VO plus A square V1 plus A V2, that is equal to ZF into IO plus IA square I1 plus AI2 plus IO. So this is your IB, this is your IC, right? Okay. So now from this equation we found that VO minus V1 is equal to ZF into 2IO minus I1 minus I2, right? So this is your equation. Now VO minus V1, I can write 3ZF equal to IO, because if we'll substitute I1 plus I2, that is nothing but minus IO, so it will become 3 of IO, so it will become 3ZF IO. So now on the fault conditions in the sequence domain, what are the fault conditions in the sequence domain? For first fault condition is IO plus I1 plus I2 equal to 0. And then second fault condition is VO minus V1 is equal to 3ZF IO. And third condition is V1 equal to V2. Now if we'll represent these three equations, three sequence equations, sequence domain equations, in the form of sequence component network, we'll represent this as like this, right? So only this positive sequence and negative sequence and zero sequence components, they are interconnected together in such a way that it will give us, it will satisfy these sequence domain equations. Okay. Now from this network, from this sequence component network, now I can write the equation for I1. So what will be I1? I1 will be nothing but equal to Vf by Z1 plus Z2 parallel with ZO plus 3ZF. That is nothing but equal to Vf by Z1 plus Z2 into ZO plus 3ZF by Z2 plus ZO plus 3ZF, right? So now I will find I2 and IO. So I2 will be nothing but, it will be just, because these are two parallel lines, right? So I can write it in terms of I1. So I'll write minus I1 into ZO plus 3ZF by ZO plus 3ZF plus Z2. Similarly, I can write for IO. IO will be equal to minus I1 into Z2 by ZO plus 3ZF plus. So this is just the law of parallel lines we can apply here. And in terms of I1, we can represent I2 and IO. So now we found the current in sequence domain. So now we can again convert back to the phase domain, right? So this is the approach how we do the fault analysis in the when the unsymmetrical fault happens, right? So because unsymmetrical fault is important and it happens frequently, many times in the network, and therefore we need to understand the principle. So it is also very important, it plays very important role in fact in relay coordination and designing the protection system. Okay, so we'll stop here. Thank you for your kind attention. So in the next lecture, we'll see the overcurrent protection schemes. Okay, thank you very much for your kind